Hello and welcome to Morehouse's Math Menagerie. Today we're going to talk about multiple regression and nonlinear regression. You will recall from previous videos that we discussed the relationship between number of beers consumed and blood alcohol concentration. We established that there was a linear relationship between these two variables, and this is the model that was produced from that relationship. However, this model is a little bit incomplete. You can imagine that there's more variables involved with your blood alcohol concentration than just how many beers you consumed. It turns out that there's a more complicated formula that uses not only how much alcohol you consumed, but also your weight and your gender as well in order to calculate your predicted blood alcohol concentration. This would be called a multiple regression model because it takes into account more than one variable to help explain our predicted blood alcohol concentration. To use this formula, we can plug in the alcohol consumed in grams, a person's weight in grams, and then a gender constant. The gender constant for females is 0.55, and the gender constant for males is 0.68. You take this number after it's been calculated and multiply by 100 to turn it into a percentage. To show the effectiveness of this multiple regression model, let's take a look at a few separate individuals. Let's say we had three different individuals who weigh 125 pounds, 190 pounds, and 250 pounds all drink 3 beers. Our simple linear model would predict that all three of their blood alcohol concentrations would be exactly the same because it only took into account the number of beers they consumed. However, our multiple regression model would show that the lighter person, the 125-pound person, had a higher blood alcohol concentration than the other two folks. You can see that as body weight increases, the blood alcohol concentration from consuming 3 beers decreases. That makes some intuitive sense since weight would help you absorb the alcohol better. Another example of multiple regression would be finding blood volume. It turns out that there are formulas for males and females to help predict the amount of blood you have in your body in liters. For males, the predicted blood volume in liters is 0.3669 times your height cubed plus 0.03219 times your weight in kilograms plus a constant of 0.604. Similar formula for females, just with the numbers adjusted a little bit. This was pretty interesting to me, so I decided to calculate how many liters of blood I have in my body. So I took my weight in kilograms and my height in meters and plugged it into the formula here for males and calculated that I have 7.22 liters of blood in my body. Now for some discussion on nonlinear regression. There are 5 main regression models that we use in statistics. The first one's linear, which we've spent a lot of time talking about. The second one is logarithmic. Third one is power. You'll notice here we have the x variable is to a power. That's why it's called a power model. We have a quadratic. You probably remember this from taking algebra classes. And then we have an exponential. The key thing to remember to help you distinguish between power and exponential is with exponential, the variable is in the exponent. In a power, it's a variable to a power. That can help you figure those two out. Now, looking through these, a logarithmic curve kind of starts out growing, almost looks like a nice curve going up, and then it flattens out. That's a logarithmic curve. Here's an example of a power curve. It has a single arc to it, and it would continue to increase as the x value increased. Exponential can look the same as a power curve. These look very similar, as you notice, to the last slide. And the last one is quadratic. You'll notice again, this looks very similar to the power and the exponential models. It can be difficult to distinguish between these, and I'm going to walk you through some examples here in a minute on how you can do that. All right, let's read through this together. An experiment involves dropping a ball and recording the distance it falls y for different times x. After it was released, construct a scatter plot and identify the mathematical model that best fits the given data. Assume that the model is to be used only for the scope of the given data, and consider only linear, quadratic, logarithmic, exponential, and power models. Okay, so the first thing we're going to do is going to click on this, but instead of opening in StatCrunch, we're going to open it up in Excel. We can do these problems in StatCrunch, however, Excel makes it a lot easier. Once we have this open, the first thing you want to do is make a scatter plot. So click Insert, and then you're going to click on this first option for your scatter plot. You'll notice we have a nice curve going up. Let's take a look at the homework. It looks like part A is going to be the answer. Let's check that. All right. Now it wants us to pick the best model, and we're given the 5 options that we discussed earlier. So going back to Excel, I'm going to select one of the scatter plot points. I'm going to right click on it and say Add Trend Line. Scroll down to the bottom. The first thing we want to do is to display the equation on the chart and display the R² value. You'll notice we end up with a model prediction here and an R². Remember that R² is the coefficient of determination, and it tells us the percent of the variability in the Y variable that can be accounted for by our model using the X variable. So the higher the R² is, the better the model. You can see it by default started us on linear, and we had an R² of 0.9718. Let's compare that to exponential. Exponential is a little bit lower. Let's compare that to logarithmic. Logarithmic looks like 0.8 something. That's not good. Polynomial is going to be our quadratic of order 2, 0.9998. That was better than the linear model. Now let's compare it to the power model. The power model is 0.9996. That's pretty close, but polynomial wins out by just a little bit. So in StatCrunch, we're going to select the exponential or polynomial equation here, and we're going to type in our values. 3.464 goes with the x². The coefficient on the x is 2.766. And the value of our constant is negative 1.21. So I need to put in here negative 1.21, and I'll put a 0 on there because they want 3 decimal places. Check that answer. It loves it. All right, the last example I want to do for you is number 4. This one's a little bit tricky because the x variable is in years. But let's read through it together. Construct a scatter plot and identify the mathematical model that best fits the data shown below. Let x represent the year since 1959, with 1960 coded as x equals 1, 1973 coded as x equals 14, 1986 coded as x equals 27, and so on. Let y represent the subway fare. So what we're going to do here, let's first things first, is open this up in Excel again. Since our x variable is not going to be the actual year, but the number of years from 1959, we want to add a column to the left in between year and subway fare. So I'm going to say insert. The reason I inserted the column in between these two values is when I select these two variables later, Excel is going to automatically count the variable on the left as the x variable and the variable on the right as the y variable. Now, to calculate the number of years since 1959, I'm going to type in an equation. So I'm going to select this very first cell next to 1960, and I'm going to say equals this cell. I'm going to select it. You see it says A2 there, minus 1959. It tells me that was 1 year away from 1959. I'm going to select that cell again, and you see this little square in the bottom. I'm going to drag it down, and it will automatically calculate how many years it's been since 1959 for all of my data. Now that I've calculated these years since 1959, I'm going to follow the same process we did on the last problem. I'm going to select our data, insert a scatter plot. You can see we have a little bit of a curve going on, but it's kind of wiggly. Let's look at our graphs. I think A is going to be the answer again. All right, it likes it. Now let's look at the model. So we're going to go back to Excel. We're going to select one point, right click, and say Add Trend Line. Scroll all the way to the bottom and say Display Equation and Display R-squared value. Again, it defaulted to a linear model. You can see that our R-squared is 0.909. Let's compare that to exponential. 0.95, so exponential is the winner so far. Logarithmic, 0.63, so that doesn't work. Polynomial, 0.93, that doesn't work. The power is 0.7827. So exponential was the best model so far. Let's look at this here and type it in. So exponential is going to be, wait, this one here, C. I kind of clicked on accident, but C is going to be our answer here. And we need to type in the equation. The coefficient is 0.1818. So I'm going to type that in here first. 0.1818. Well, 1 and 3 decimals. I actually need to round that to 0.182. Sorry about that. Going back to my model, you can see here it says e to some number. That number is really hard to read. So I'm going to select that, go back to home, and I'm going to increase the font like size 14 or something. You can pick whatever you want so we can read this number here. You'll see it says e to a power times x. The e to the power is the value of the base of the exponent. So we actually need to calculate that on a calculator. So on your calculator, we're going to want to take e to the 0.0535 power. And on mine, I get that value is 1.0549, so 0.55. Let's check that answer. Awesome, it likes it. I hope you enjoyed the video. Thanks for joining us. Have a great day.